This next section of the course is going to be all about the phase behavior of materials. So we're going to start with gases because that's what we've been using so far. All of the working gases in our engines. We haven't had anything in the condensed phase, liquids or solids. It would be great to figure out how to use liquids and solids in some sort of engine system, but all of our engines are based on gases. You heat them up, they push on things. It's that simple. Okay, even our most technologically advanced power plants, like nuclear power plants, are still just using steam. They're just using the heat from the nuclear decay, heating up water and spinning a fan that spins a generator. So if you can solve that, like if you can figure out how to more directly get the power out of the nucleus, then I mean, it would be an amazing feat, you know. And lots of people have tried. So, but still, who knows, right? I mean, the speed at which those particles are coming out of the nucleus is unbelievable, and it's slowing down. And when it's banging into the water, that's what's heating up the water. Okay, and so there's lots of things going on that we just haven't been able to capture yet. So that's gases. Now we're going to start talking about condensation. So let's go back over some of the standard conditions. So you've heard of STP. Whenever we're dealing with gases, we have STP, but we also have SATP, standard ambient temperature and pressure. And this is the thermodynamic definition of standard conditions that's in the tables, like the thermodynamic tables that we used on the last exam. So SATP, 298 and 1 bar. 1 bar is 100,000 pascals. And 1 atmosphere is 101,325 pascals. So that's that defined term that you've seen before. And so a bar and an atmosphere are very close to each other. They're about 1% different. Okay. You've seen bar a lot because you a lot of the pressures in meteorology are listed in bar, and then also they use inches of mercury sometimes. And then we have the molar volume. So at room temperature and 1 bar is 24.789 liters per mole. And then standard temperature and pressure. This is STP. This is what we typically used in the freshman chemistry course, Chem 2. And think about this. This is older, and because it's older, think about the ability to control the pressure and temperature of gases. They used ice water, and so that's why this is at 0 C, because it's very simple to take a balloon. You want to measure the volume of the gas in that balloon at a particular temperature. How do you control the temperature of that balloon? It's pretty difficult if it's out here in the air. If you put it in ice water, then you know it's at 0 C. And you got 1 atmosphere of pressure, so then you mark the mark, you pull the balloon out, and you mark the mark, and then you measure the displacement volume. Very easy to measure the gases and their volumes using STP. So STP, the molar volume is 22.4. So many people have that number memorized, and I want to go through this specifically because whenever we're doing conversions from liters to moles and moles to liters and things, a lot of people will use this one here, you know, the STP molar volume, because they remember it from freshman chemistry, 22.4 liters per mole. But they'll be using it in the situation where it's room temperature, and that's wrong. So don't be caught by that. Room temperature molar volume is 24.7, so you're quite a bit off. And so that's the source of some people's errors. Okay, let's talk about gas mixtures. If I'm measuring the pressure of air in this room, one way to do that is to go, say, put a pressure sensor in the wall, and essentially it's a little sensitive area that measures the force that the gases hit that wall with. And whether that's a nitrogen or an oxygen, it doesn't matter. It just measures how much force is being put on that square area. So the total pressure would be the sum of the partial pressures. The partial pressures are the pressures of each individual of those gases. And so the pressures exerted by a mixture of gases is just a sum of the partial pressures of those gases. So the PA is the partial pressure of A, and PB is the partial pressure of B, and P total is the total pressure. So that's Dalton's law, and we're going to use that a lot in this is the third part of the course, in the fourth part of the course when we get into mixtures. But this is the first introduction of it. And so like if this was the mole fraction of oxygen down here, let's say O2, and we just thought about there being really only two components. So this is 20%. So this would be the partial pressure of O2, and the 80% the partial pressure of N2, and the total pressure would be 1 atmosphere. So this would be 0.8 atmospheres, and this would be 0.2 atmospheres. Mole fraction. So mole fraction, I did 20 instead of 0.2. It really should be 0.2. It's a mole fraction. You can multiply it by 100% and so show that it's 20%. So this is an example of our atmospheric composition. Now, you know, we're pretty much fixed at this value just by the structure of the Earth and our atmosphere. So, but you can make any mixture of oxygen and nitrogen, and you could go all the way to 100% oxygen or whatever. So we talk about the mole fraction. That's the partial pressure of that particular substance divided by the total pressure, or the number of moles of that substance divided by the total moles. Okay, and so then Raoult's law, if we knew if this was above a liquid, so I'll circle this. If it's in contact with liquid A, and we know what the vapor pressure of liquid A, pure, liquid A, then that would be the vapor pressure of liquid A. And then if we had just a small portion of that substance in a mixture, then it would be the mole fraction of A would give us the partial pressure of A. Okay. So this part here, this vapor pressure is the pressure of A when it's in the pressure of A gas if in contact with liquid A. So that would be like a pure substance. You've got A in a container and the liquid's at equilibrium with the gas. That would be the maximum vapor pressure of that liquid. Now, if you have a separate container where you've got 50% hexane and 50% decane, right? Then the maximum values of their pressures would be 100% hexane in contact with the liquid. That would be the maximum hexane value would be. If it's 50%, it would be 50% of that maximum value. And decane, again, it would be 50% of that. And we'll get into all of that in the mixtures chapter. So for now, let's set this aside. I just wanted to really emphasize this one here, Dalton's law, and the idea of mole fractions. Okay, so let's think about how molecules interact, especially in the gas phase. They bump into each other. And when they bump into each other, if they're an ideal gas, they have no attractions and infinitely hard collisions and no volume. Okay, so what do we mean by no volume? Well, this would be sort of this is, say, the nucleus, and this would be the radius of the particle. Okay. because that's what we would say is contacting. So do you remember, let's see, I don't know if I've said it in this course, but certainly in the PChem 1 course, that red ball at target, if that was a hydrogen atom, if that red ball was a hydrogen atom, or it was a hydrogen nucleus, so 1 proton, the electron would be in Madisonville, or in Spring, or over Navasota, or past Lake Livingston. So this would be the outer edge of that electron cloud. Now, ideal gases, we say, have no volume. So this is what makes up the volume. This outer edge of the electron cloud equals the volume of the particle. Okay. And so they would hit. When their electron clouds touch, they would hit. That's what we mean by contact here. But notice the ideal gas goes to the actual coordinates of the nucleus. So ideal gases, we ignore the electron cloud. They have what we call infinitely hard collisions. There's no floppiness to the molecule at all, or atom at all, and I will say no volume. No particle volume, I'll say that. No particle volume. So if you have 50 particles in this room, they wouldn't take up any of the volume of the room. They would just have locations. They're called point masses. So like whatever coordinate this would be, if I had a particle there, it wouldn't take up any volume at all. So all the other particles have 100% of the volume of the room. This particle didn't take up any of it. Okay, but a real gas, we've got to reduce the volume of the room a little bit, because real gases take up space, and they're going to hit each other, and they're going to actually be attracted to each other. So real gases have some attraction, and so you see down here attractions are dominant. How is that happening? Well, electron clouds are floppy, and so if we're coming close together and my electron cloud sees yours, one of those electron clouds is going to flinch first. Okay, and slide to the other side of the molecule. When it does that, then your positively charged is facing me. I can see the nucleus, and so my electron cloud sloshes a little bit towards that nucleus. That's an attraction. And then sometime later, my electron cloud is elastic, so it slides to the other side of my nucleus a little bit, and then your electron cloud slides forward. And so when these electron clouds start oscillating with each other, then those are attractions. And those are called van der Waals attractions. We call them London dispersion forces. If there's a dipole moment, then the positives and negatives in the molecule aren't balanced, and so we would definitely get attractions there. If there's hydrogen bonding, we get attractions. So there's lots of ways the molecules could attract each other. But if you stick them in a small enough container, eventually the molecules are too close on average, and those nuclei start to repel each other. And so that's what's happening here. Repulsions are dominant when we get the molecules too close to each other, or atoms, and you see this repulsive area here. So that's a little bit about how molecules are interacting in space. So if you get molecules on average really far apart, like right here, so remember this is the separation axis, then they behave ideally, even though they're not ideal, right? So this is the real gas here, this blue curve, and it approaches the ideal gas curve at long distances. So how do we get molecules far apart in a room? We lower the pressure or expand the volume, okay? So if there's not a lot of molecules in there, then they're pretty far apart and they behave ideally. You start cramming more molecules into a small space by reducing the volume or by increasing the pressure. How do we increase the pressure? Well, by driving more molecules into that space. So we pump more molecules in, they're going to be closer together, and eventually they start attracting each other and they'll condense. They'll get so attractive that they'll start to form pairs and triples and quadruples, and they'll just start to form droplets, and then they'll condense. Ideal gases never condense because there's never any attractions. So that's a failure of the ideal gas law, is this idea that we could have condensation. So here's Boyle's law, this PV equals constant for an ideal gas, and these PV curves are called isotherms. We've already dealt with them. And on these isotherms, you would have things called adiabats. And so you could have a Carnot cycle here like this. So we've already dealt with isotherms. We've dealt with adiabats. And so there's like a little Carnot cycle. But these, if we keep it cold, so we keep the pressure low and we decrease the volume, then we might be able to squeeze these molecules together to where they form a liquid. And so what happens if the gas condenses to a liquid? Let's plot that case, okay? So here on the next slide, let's pretend that at this point here, we form a liquid. And this is the vapor pressure. So what is the vapor pressure? It's the pressure above a liquid that's in equilibrium with its gas. So over here, this is the gas area. We're coming along this isotherm. We're compressing it with a piston, if you want to think of it that way. And then we get to this point, and we're at the maximum vapor pressure. So we're at the pressure that the gas would have above its pure liquid. And so if we keep pressing on it, it's going to form a liquid. And so way over here, I'm just going to draw it like right here. At this volume, we form a little liquid drop. So we still have gas at this volume, we have liquid at this volume, and we have this region here in the middle that is the equilibrium region. And so that's what's being shown here. See, like this point A here, it's shown here that this is the volume of the vapor, pure vapor at that temperature. This is the volume of pure liquid at that temperature. If we were to try to shrink the volume below this, then the pressure goes up dramatically. So we're taking a liquid and we're just squeezing the liquid. There's no vapor anymore. And so these dashed regions give us the vapor pressure. So this is PVAP at 0 degrees C. And this one, 60, is PVAP it looks like 20 degrees C. See, the 20 degree isotherm comes up here, and then it hits this point, and you start to get condensation. And the volume of the liquid is at E, and they have this vapor pressure equilibrium, PVAP. Now, there are some temperatures at which you won't get a liquid. Okay, it's just too high. And so that's what these are. These are above the critical temperature. 50 degrees C, 40 degrees C. For CO2, you don't have any liquid phase at those temperatures. It's just too hot. And so there is a temperature, a critical temperature, below which you can get a liquid, above which you cannot get a liquid. And so we'll see those in a minute. What, you know, but essentially the critical temperature here is, there's a critical pressure, and there's a critical volume. Come down here. And every gas will have its own critical values: critical volume, critical pressure, critical temperature. So here's an experimental one that says the data for CO2. And I like this figure because it shows the ideal gas at 334. That's this dashed line. And here's the experimental isotherm for 334. So here at 0.3 liters per mole, this is what the ideal gas pressure would be, and this is what the actual pressure would be. So the actual pressure is around, let's see, so this is 70 here. So this is a little bit below that. You want to say 67? And the predicted ideal gas, this is 90. So it's a little bit above that. I'm going to say 92. So what's our percent error? So we'll take 92 minus 67. And then what do we divide by? We divide by the more accurate one, okay? So the more accurate one is 67. Okay, so we have 267 minus 67 divided. So we're 37% high. Pretty bad error. And that's at 334. If we were to raise the temperature, those lines, or if we increase the volume, look, the percent error down here is not that much. But at that particular volume, 0.3 moles per liter, or liters per mole, the error is high because we've compressed it into a small space. If we expand that volume, our error decreases and the gases start behaving more like an ideal gas. Okay. As we compress it more and more, you see it behaves much less like an ideal gas. Look at the percent error here, 140 versus 85. You know, much larger gap there. Okay, so these are isotherms. All of those lines are isotherms. The ones that are above that orange region are all 100% gas isotherms. The ones that intersect that orange region show the condensation area. Okay, so this is the volume of the gas at 258 Kelvin and whatever 47 bar, and this is the volume of the liquid. So if I wanted to know the density of the gas phase at this area, I could come down here, and that is what do you say? This is 0.3, 0.4, 0.32, 0.32 liters per mole. Okay, and density is equal to mass over volume. Okay, so here's the volume. What's the mass? Well, this is CO2, so it's 44 grams per mole. The per moles cancel, and I've got the density. It looks like, yeah, 0.32. So 44. So that's 137 grams per liter. Is that right? Come on, where are you? 138 grams per liter. Okay. If we were to do it per milliliter, it would be 44 divided by 320. .138 grams per milliliter. Okay, now let's do the liquid density. So this is around 0.95. I don't know, what would you say? No, 0.095 or 95 mils. So 44 and 95. So 0.46. So you can see that the liquid is much more dense than the gas, 0.46 grams per mil versus 0.138. Okay, and so you can get this kind of physical information from these phase diagrams. In fact, a lot of the physical information is how we make the phase diagram. We measure densities of these things, and then we put those points on there, and then we connect them with isotherms, etc. Okay, so this region way out here to the right is the gas region. Way over here on the left is the liquid region. And if you're up in this region where you're at a really small volume, a really high pressure, and a really high temperature, that's called a supercritical fluid. So maybe you've heard of that term. We've got supercritical fluid chromatography now, which is a really great technique. And it's weird. It has the density of a liquid, but flows like a gas and has no meniscus. So it's a great solvent, right? It has the density of a liquid, so it can dissolve things, and yet it fills the whole container. There's no meniscus. It doesn't settle at the bottom like a liquid does. So it's not a liquid, but it's not a gas either. It's got the density of a liquid. That's why we call it a fluid. We really don't know. It's a fluid. It flows, right? But it's not liquid because there's no meniscus. That's what we would say is a liquid, right? It takes the shape of its container, but it doesn't completely fill the container. But a supercritical fluid does completely fill the container. So that's just a weird thing. We don't really have a short phrase for it, so we call it supercritical fluid. That's what you got. Okay. Now that's a great technique. We use it to dry clean clothes now. We use it to decaffeinate coffee beans. So you can put your beans in a big stainless steel vessel and keep pumping CO2 into it until it gets into the supercritical region, and the caffeine and maybe some other compounds come out. I don't know, but it dissolves the caffeine. The reason I'm worried about the other compounds is because it does taste different. I think decaffeinated coffee has a slightly different flavor, and I don't know if they've dissolved some of the molecules out that I like on my taste buds, and they're not there, you know. I don't think caffeine has a taste itself, but there's other things that may be dissolving in it. And then you just pop the valve, and that liquid or fluid will flow into another container. And then if you want to get the solute out of the solvent, you lower the pressure and let the CO2 go into a recovery area. It's a gas, and the caffeine stays there and drops out as a crystalline solid. It's beautiful. Yeah. There's no toxic solvents or anything like that. And so then you can sell the caffeine to Monster, and you can sell the decaf to Folgers, and it's a great process. And you recycle the CO2. So that's one of the best processes out there. Same with grease on your clothes. You can put all your clothes in a big stainless steel vessel, pump in the CO2, dissolve off the grease, let that flow over here, pop the vet pressure, and the grease just drops out of solution. The clothes are clean. They've never been impacted with soap, harsh chemicals, no allergens. It's expensive, right? But yeah, so it's a great way to go. So this PC, VC, and TC define that critical point. So those substances above TC are called supercritical fluids. Okay, if they're in a small enough volume and a high enough pressure. So you can be above the critical temperature and be a gas, like an ideal gas region, because you're in a big container. So we wouldn't call oxygen and nitrogen in this room a supercritical fluid because it's not a high enough pressure. Okay, they are definitely way above their critical temperature, but they're not in a small enough container at a high enough pressure. So the pressure and volume relationships are also needed to define a supercritical fluid. Here are the critical constants of gases. So we were just talking about CO2. So here's the critical temperature of CO2. It's very close to room temperature, 304. We need to squeeze it down into a small volume, 94 mils for every mole of CO2. And then we need to crank the pressure up to 73 atmospheres. So that's quite a high pressure. And in that region, small enough volume, large enough pressure, high enough temperature, you can have a supercritical fluid. We'll talk about this boil temperature in a second. But look at hydrogen or helium. Helium, you only have to go to 2 atmospheres of helium, but you got to cool it down below 5 Kelvin, or you've got to be, anyway, once helium is above 5 Kelvin, it can no longer form a liquid. It can only form a supercritical fluid. You have to squeeze it into a fairly small space for every mole, and then you don't have to pressurize it very much. So these are physical properties of molecules, and look how different they are. I mean, you know, some of them have a really high pressure, like ammonia, okay, and some have a really high volume, like hexane. So it's really interesting to me to look at all these different critical constants. Here's here's water. It seems like the hydrogen bonding ones need a high pressure because you got to, yeah, if you have a high enough pressure and low enough temperature, you can have a liquid. But if you get above 647 degrees Kelvin for water, you could never have a liquid water above that temperature. Okay, so let's look at this compression factor. This is a way to measure the ideal or non-ideal nature of gases. So this Z compares real to ideal behavior. So look at this equation. This is, see, I thought with the ideal gas law, PV is equal to nRT. So what's the ratio of PV to nRT? Well, it would be 1 for an ideal gas. So you see here, Z is 1 for a perfect ideal gas. So if you put a real gas in here, and how would we do this experiment? It's pretty easy. We typically take a fixed volume, like a stainless steel vessel, so it's non-reactive. We stick a known amount of moles of gas in there at a given temperature. So we know the volume, we know the number of moles, and we know the temperature, because those are easily constructed. And then we measure the pressure. So we have a little pressure gauge on there. And it should, if it was ideal, this ratio should equal 1. Sometimes the pressure is lower than we expect. If the pressure is lower than we expect, then the gas is attracted to itself. Right? We stuffed a bunch of gas in there, fixed volume, fixed temperature, and we know how many moles there are. We expect a certain pressure, and it's too low. We're like, what's going on? Well, the gases are attracted to each other, so they're not hitting the walls. They're not hitting the pressure gauge. So that's what's going on in these regions here. You see these regions where these lines are below 1? So these are attractive regions. But what if we measured the pressure and it was higher than we expect? That means the gases hate each other. They'd rather bang into the walls. So they're getting away from each other. So hydrogen hates other hydrogens. Look at that. Hydrogen gas does not, it's the least compressible gas. And there are, if you put enough gas in there that you get into the high pressure regions, then these gases become repulsive. So methane, ethene, ammonia probably turns around and does it too, but these up here are repulsions dominate. Okay. So the boil temperature is that temperature for a real gas at which the slope goes to 0 at low pressures. So you see this region, the boil temperature, it's where the gas behaves as an ideal gas for as long a range of temperatures as it can be. Okay, so that's the boil temperature. So it's not a huge thing, but I just wanted to show you that at high temperatures, the repulsions dominate. At lower temperatures, attractions dominate. There is a temperature at which that slope just slides right in to 1 as the pressure goes to 0. Let's talk about the theory of corresponding states, though. This is pretty awesome. So all the gases have different critical points and different Z values, compressibility factors, as shown here on this graph. But if we were to take the pressure of, say, hydrogen and divide it by its critical pressure, and the pressure of methane and divide it by its critical pressure, and the same for the volumes and the same for the temperatures, could we get all of these gases to fit on the same curves? In other words, does the critical pressure, temperature, and volume capture the differences in the gases? And the answer is yes. Okay, so look at this next one. So here is the Z value. This is experimental data in this curve. So this is the Z value. And notice that this is T over TC. Okay, for this one right here. It's 1.2 for this curve. And what are these gases? Well, this is nitrogen, methane, propane, ethene, and they're all on the same curves. So this is the reduced pressure, which is equal to the P over PC. And this is the Z value, which would include that V over VC. And this is the T over TC, and they all fall on the same lines. So this is telling us that those critical points capture the differences in all the gases. This is also an engineering trick, I would call it. And notice that this pressure axis actually has no units. So if this was millimeters of mercury on top and on bottom, they would cancel. So some engineers will call this unitless pressure, which blew my mind the first time I saw it. And this is unitless temperature. I saw this engineering chart when I was working in industry, and the x-axis was unitless temperature. And I thought, what on earth does that even mean? How can you have a temperature that's unitless? And so I didn't know this engineering trick back then. This is what's going on here. So you're taking the pressure relative to some other kind of pressure, and the temperature relative to some other kind of temperature. And to be honest, all of your equilibrium constants that you've used to this point in chemistry have really been unitless concentrations. So your molar concentration that you would measure to make up an equilibrium calculation was really divided by a standard molar value of 1 molar solution. So it cancels all the units on all of those molar values and gives you a unitless equilibrium constant. Because the equilibrium constants are unitless. How can that be if I've got the concentration of A raised, squared, and the concentration of B cubed? Well, each of those concentrations are divided by the standard concentration of 1 molar. So all of the units are gone. We just don't tell you that. I think we should tell you that. Okay, so let's look at this, how these reduced variables are used. Remember our QSPR exercise, the automobile fuel exercise. At what temperature and pressure would hydrogen behave like hexane at 1 atmosphere and room temperature? So hexane's a major component of gasoline. And so we could look at hexane at 1 atmosphere, and its unitless pressure would be 0.03. We divide by the critical pressure for hexane. So we go to that table, find hexane, grab its critical pressure, and so its unitless pressure would be 0.03. The unitless temperature would be room temperature divided by its critical temperature, 508. And so its unitless temperature would be 0.587. And now the hydrogen, if we wanted it to behave like hexane, we would use the same reduced variables. But because hydrogen has different critical points, this would tell us what the actual temperature for hydrogen would be. So here's the pressure using that same reduced pressure or unitless pressure. It's got a different critical pressure. So we would have to operate at 0.4 atmospheres, and the temperature, same reduced temperature, we would have to operate at 19 Kelvin. So if we were on a frozen planet, say orbiting Jupiter, Europa, okay? I don't know what the temperature of Europa is, but if it were 19 Kelvin and the atmospheric pressure was 0.43, we could use a gas pump for the hydrogen. We could stick that in our tank and pull the handle, and liquid hydrogen would flow in to that gas tank, just like liquid hexane flows in today, in our atmosphere and our pressure. So I think that's kind of neat. It shows how unrealistic that is for using just the regular gas pumps to dispense hydrogen at our temperature. The temperature is the thing that really kills it. All right, we're out of time. This is a good break, but we're going to be talking about condensation and vapor pressure next time, and this is today's lab. So y'all are going to be doing this van der Waals equation of state and correcting this area and correcting the van der Waals equation so it can take into account condensation. So you'll be working with PV diagrams in this week's lab. And I'll talk more about this on Wednesday. Okay?